For the video recording, I need to be sitting down, otherwise the camera doesn't get the top of my head. So this is why I'm sitting down here. I'm going to talk about these things called Profunctor optics. This is work that I've been doing with Matthew Pickering and Nicholas Wu. Matthew is an undergraduate student of mine. He did his project on this, and it's very nice work, but it's mostly his work. And I get to give the talk about it. So what this is about is lenses for access into data structures. So a lens, the easiest thing to think of with a lens is if you have a pair with two values, a left value and a right value, you might want to have access onto the left-hand value in that pair. And particularly you might want to be able to get the left-hand value from the pair and then to set a new left-hand value in the pair. So there's two functions involved, a getter and a setter, to get access onto the left-hand component of a pair. So lenses do this for any product type. It can be a field of a record, it can be the third element of a list. So any projection works through a lens. But there is a dual to this. For some types, these things are called prisms, and I'll show you concrete definitions of these and examples later. And lenses and prisms have collectively been called optics, and there are some more things within the remit of optics. There are also things called adapters and things called traversals, and I will also tell you what those things are. And there are two problems with the obvious way of representing these, where you represent a lens as the two functions, the getter function and the setter function. One problem is that these optics are not closed under what are called heterogeneous composition on the slide. By that I mean you might want to put together a lens and a prism. A lens will give you access into part of a product type, and maybe there's a sum type within that. So to get access within a sum within a product, you would hope to be able to compose a lens and a prism somehow, saying how to get through each part. But the problem is, the thing that gives you access into a sum into a product is not a lens and it's not a prism, and I'll show why that's the case. So you can't express that as a lens and you can't express it as a prism. These things are just not within the language of expressible stuff. And a second problem is, suppose you wanted to put together a lens with another lens. So you've got access within the left-hand component of the pair, and maybe that is itself a pair, and you want to get at the left-hand component of that. So it's the left component of the left component of a nested pair. That is a lens, and you can make it out of putting together two lenses, but it's a bit clumsy to do so. You have to take the lens apart into its getter and setter functions. So they do compose homogeneously, but only in a clunky way. So I'm going to fix both of those problems by showing you a different representation. And this representation is in terms of these things called profunctors, which are rather cool. And it's a very slick presentation, and it will allow us to compose lenses easily with other lenses, and more importantly, to compose lenses with prisms and lenses with traversals and adapters with prisms and so on. So you'll get much better compositionality of these data access mechanisms. So I call this modular data access mechanisms. So this is one way of looking at this is a kind of bidirectional programming style. You express the getters and the setters in one go by saying whereabouts in the structure you are. It's kind of like a pointer into a structure. I've been doing some work recently on bidirectional programming languages which let you express in one go a program that can be read in two different directions, sort of the get direction and the set direction. But I recently discovered that, it occurred to me that a nice logo for this is the former British Rail logo. Now maybe you can't see this if I'm sitting down, but here's my my bidirectional T-shirt. So here's here's lenses. The getter and the setter I've called view and update here. If you have a structure S and it has an A component within it, the view function the view function is a function from the whole structure S to the component. It extracts the components within it, the A. And if you want to change that component to a B and put it back, you'll get a new structure which will be might be of a different type, T. So the update function takes the new component B and the old structure in which it appeared, S, and produces a new structure. So maybe this is an integer character pair, and you take out the integer and put a float in its place, then you'll get a float character pair as the result. So the output type might be different from the input type. So I've captured this as a piece of Haskell. It's a record with two fields, each of which is a function. And there's a picture at the bottom right of the slide that shows those two functions. So the view function is just a plain ordinary function from S to A, and the update function takes two inputs. It takes a B on the right-hand side and the old S on the left-hand side and produces a T as the result. So in the middle of the slide is an example lens. This is the lens onto the A component of an A cross C pair, and the view function gives you the first component of the pair, and the update function takes a new value for the first component of the pair and an old pair and throws the old left-hand component away and puts the new left-hand component in its place. So, I'm going to call that lens pi1. So that's lenses. The dual, prisms, is for sum types. So a sum type, think for example an object-oriented superclass with several concrete subclasses, and a prism will give you access to one of these things as the subclass. So maybe you've got shapes and you've got squares and circles, and you've got something that you want to do to a circle, and what you're given is a shape. So it's got the wrong type. So you need to get access to that thing as a circle, and so there's a downcast method that will give you from a shape to a circle, and an upcast from the circle back to the shape again. So here it's dual, so it's the other way around. It's the upcast that is the obvious thing. The upcast always succeeds. So I've called that build here. That takes the value that you've changed it into and upcasts it back to the enclosing type, the context. Matching is the complicated thing. So matching, like downcasting in OO terminology, might fail. You might have a shape and try to downcast it to a circle, and it might be a square. The downcast might fail. This generates a sum, whereas the lens, the update function, consumed a product. So that's the duality coming through. And if you look at the bottom right-hand corner, the picture is very similar. Here we've got an arrow going across the top, and looks like a curved arrow going back along the bottom. Actually, it's a funny arrow going across the top with two heads, trying to show the fact that it might go in one of two different directions, and it's an ordinary arrow across the bottom. So the difference is just the slight difference in where the curved bit goes. Maybe that's helpful, maybe that's not helpful. In the middle of the slide is an example prism. This is the context is an optional value. So in Haskell, that's a maybe A. So I have an optional thing of type A, and that's either just an A or nothing. And I want to do some A stuff to it. So I want to get the A out of this optional thing. So the matching part will give me an A if there's one there, and otherwise it sort of heads straight for the exit and gives me a maybe B if there was no A there. So if there was no A there, you've got nothing, and nothing is of type maybe A, but nothing is also of type maybe B. It's a polymorphic constant. So downcasting will give me the A if it's there, and sort of exit if it's not there. And upcasting is easy. That takes an A, takes a B, and makes a maybe B just by wrapping the just constructor around it. So this is an optional B that is there. So that's easy to do. So this prism, I've called it the, gives you access to the element of an optional type. I'm going to briefly mention the other two. I'm not going to say very much about them. Adapters are the common specialization of lenses and prisms. So here, think of a lens where you get access to the whole thing. But so the useful cases for this are where you have to do some data conversion. So maybe you've got an operation that works on triples, XYZ triples, and what you've got is not quite a triple. It's an X comma Y comma Z nested pair. So if you want to do your triply thing on this nested pairs, you need to adapt the nested pairs to a triple, then you can do your triply things, and then you adapt it back again to the nested pair. So adapters work like that, and you can think of adapters as lenses where you get the whole thing, so the update doesn't need to take the old context because you're going to overwrite the whole thing. You can think about them as degenerate prisms where the downcast always succeeds. So there's no need for the sum type in the matching. So adapters also fit into this these pictures of data access. And a fourth variety is these things called traversals. So I'm not going to explain the types and applicative functors here. If you've seen this before, this will be familiar, and if you haven't, then nothing I say within the few minutes I have available will make it clearer. But think roughly of a traversal as giving you access to several A's at once within an S structure. So this is a container type S, and it has some A's in it, and you want to be able to do things to each of those A's, one after the other. So you can get them all out, and then you can replace them with some B's instead. So if I have a list of A's, I can get all the A's out, and I can put a bunch of B's back in. The pictures suggest that both of those fit within the framework. I haven't shown you, well, it's not obvious from the type of traversal how that one operator traverse is somehow analogous to the getter and setter, but take it from me, it also fits. You can see it in the picture. From an S, I can get a bunch of A's out. This is shown as A to the N, so some number N of A's, and I can also take the same number of B's and the data structure and overwrite all the A's with B's. So I can set a whole bunch of B's at once in this data structure. So those are optics: lenses, prisms, adapters, and traversals. Here's the problems. So the first problem is a homogeneous composition. So here we have a nested pair. Let's see, it's an A cross C cross D nested pair, and you want to get access onto the A in that. So there is an A in there. There should be a lens that gets it out, and indeed there is a lens. So I've called this pi 1, 1. It gives you the left-hand component of the left-hand component of a nested pair. And you can make it out of accessing the left-hand component of a pair, so out of pi 1. So the first line of the definition there says, we had this pi 1 earlier, let's match against it and call the two functions v and u. So v gets the left-hand component of a pair, and u updates the left-hand component of a pair. So for a nested pair, it's obvious what to do with the getter. You just compose getters. So you get the left-hand component of the overall thing, and then get the left-hand component of that. So it's just the original getter twice, v compose v. So the view function for this lens onto the left-hand component of the left-hand component is just the composite of the two view functions. That's easy. That works. That's fine. It's the update that's the problem, because what you need to do with your nested pair is extract the left-hand pair out of that, update the left-hand component of that left-hand pair, and then put it back in again. So you need to use the getters in defining the composite setter. So you'll see in the definition of update there, it uses u twice, the update for a pair, but it also uses v once. So that's a bit clunky. Why couldn't we just compose the update functions? But it's necessary. That's what you need to do. In fact, for accessing for setting the left-hand component to the left-hand component of a nested pair, it's easier just to ignore what you knew about pairs and build it from scratch. The update function at the bottom of the slide does it in one go using pattern matching, and that's just an easier way of doing it. So that tells me that my abstraction was not a very good abstraction because it's not convenient to use it. It's more convenient to ignore it and go back to first principles. So that's problem 1, homogeneous composition. Problem 2 is heterogeneous composition. Suppose I have an optional pair, an optional AB pair, and I want to act on the A in it. So there might be an A there, but there might not. If the optional pair is there, then there is an A in the left-hand component of the pair. But if the optional pair is missing, there's no A. So that means you can't define the view function. The view function would have to take an optional A cross B and always give you an A. And it can't fulfill that promise. You can't always get an A out of that. So there's no way of writing a view function, so there's no way of writing it as a lens. Conversely, there's no way of writing it as a prism either, because you would have to have a build function, and that would have to, from an A, construct an optional AB pair. So the optional part is no problem, but where does the B come from? You can't use your A, so the only thing you can do is throw the A away, and that wasn't what the build was supposed to do. So the thing that gives you access onto the left-hand component of this optional pair, the A in maybe AB, is not the lens and it's not a prism. And it's not an adapter and it's not a traversal either. So it's the universe of data accessors that I've shown you is not closed under this kind of composition. So we're going to fix that. And we're going to fix that with these things called profunctors. For profunctors, just think of things like functions. They're a generalization of functions. So think of them as a blob that takes stuff in and produces stuff out. So functions you can think of as a blob that takes stuff in and produces stuff out. Profunctors are generalizations of this. They're transformers that take stuff in and spit stuff out. But they needn't take just one thing in and put one thing out. Plain ordinary functions from A to B form one profunctor, but also functions that consume A's and produce B's and Booleans, B, Boolean pairs. They consume A's and produce B's and some other stuff. That's also a profunctor. Similarly, the function that takes an A in and produces a pair of B's out. And as it happens, something that takes a pair of A's and produces one B out, that consumes A's and produces B's. So these pictures, I hope, will give you the idea. It's blobs that take some A's in and produce some B's out. So in Haskell, I capture that by a type class. Type classes are the way to do implicits, as we saw this morning from Martin Adersky's talk. P is a profunctor if it supports this operation called die-map. Now, profunctors are these two-argument things. They're parameterized by the A type and the B type. So what you need to be able to do is do a kind of like a map, but for these profunctor things. And what's going on is that I want to be able to turn a profunctor that consumes A's and produces B's into another one that consumes A primes and produces B primes. And if you think about it, in order to convert the PAB into a P A prime B prime, I need to be able to stick an adapter on the bottom of the picture that turns B's into B primes, and an adapter on the top of the picture that converts in the opposite direction, turns A primes into A's. So if I have a way of turning A primes into A's, and then a transformer that consumes A's and produces B's, and then another way of turning B's into B primes, overall I have a transformer that turns A primes into B primes. And there are some laws that these things should satisfy, just like the F map for the functor class should satisfy some laws. I'm not going to show you the laws. You can read the paper and find out more about them. But they are what you expect. Profunctors are a generalization of functions, so functions ought to be profunctors, and indeed they are. If I've got a function from A to B and a way of adapting A primes to A's and B's to B primes, then I can make a function from A prime to B prime just by composing these three things. But also, if I have functions from A's to pairs of B's, or functions from A's to B comma bools and various other things, they are profunctors too. So that's the definition here shows how to write functions of the form A to f of B, where f is a functor. So think A to collection of B's somehow. How to write that as a profunctor, and so in particular how to write the die map for things of the form A arrow f of B. So these profunctors, you can think of them as just think of them as transformers. They take some A's in and they produce some B's out. And I'm going to use two variations on that, which I call Cartesian and co-Cartesian profunctors. I can capture these things in Haskell, and they again have some mathematical properties. There's some laws that should be satisfied. But maybe just look at the pictures. A profunctor is Cartesian if, given a transformer that can turn A's into B's, you can also pass some C's around, sort of around the outside of the box. So that's what the top picture shows. The C's go around the outside of the box. And some profunctors you can do that and some you can't. And what you need to be able to do is provide this function first that shows how to thread the C's around the outside of the box. So you get a box that takes AC pairs in and does the transforming on the A to make B's, but leaves the C's untouched. So you get BC pairs coming out. Similarly, a co-Cartesian thing is something that deals with sums rather than products. So what comes in is either A's or C's. And if it's A's, you transform them into B's, and if it's C's, they just go through. So what you get out is either B's or C's. And what you need to do is provide a function that will do the plumbing for that. And as you might expect, functions, as well as being profunctors, they're Cartesian profunctors and co-Cartesian profunctors, and it's easy to define the first and the right combinators for functions. The definitions are there on the slide. So here's the new representation. It's a higher order representation. I'm going to represent these optics. I'm going to represent lenses and prisms and adapters and traversals as not these transformers, not as blobs that takes A's in and B's out, but mappings between transformers. So it's one of these optics is a way of turning a transformer that consumes A's and produces B's into a transformer that works in context and consumes S's and produces T's. And the picture shows what's going on, I hope. If you've got a blob that consumes A's and produces B's, and a context with S's in, you can extract some A's from that, feed them through the blob, get some B's out, and then stick them back in, and T's will result overall. So an optic is just a function that takes a PAB transformer and lifts it to being a PST transformer. And the different kinds of optics, the lenses and the prisms and the adapters and the traversals, are going to work by imposing stronger and stronger constraints on what the P should be. So P will be at least a profunctor, but for some of them we want it to be a Cartesian profunctor, and for some of them we want it to be a co-Cartesian profunctor. For some of them we want it to be both. But the neat thing is that if I can pull this off, if I can capture lenses and prisms and so on in this style, then I've captured them just as functions. They are functions of type PAB to PST. And if they're just functions, then you can compose them. Rather than big records with pairs of functions which don't compose neatly, these are just functions and they will just compose by function composition. So that will solve my homogeneous and heterogeneous composition problems. So here's how to do it. Let me start with adapters. The first line there is just a reminder of what we had for adapters. An adapter is a pair of functions, one that takes an S in and rearranges it to make an A, and then the to function takes an updated one, B, and unrearranges it to make a T. And the Profunctor representation of these things is just one of these optics, so that's a function that takes PABs to PSTs that works for an arbitrary Profunctor. And these two types are, in fact, completely isomorphic. If you've got an adapter, you can make an adapter P, and if you've got an adapter P, you can make an adapter, and the transformations in both directions are each other's inverses. The transformations are short, so they're in the middle of the slide there. They're just very cryptic one-liner things. So it's not obvious how that works. It certainly wasn't obvious to me when we came across these things that this is going to work at all. I think it's quite surprising. But they are very short and simple, so there's not a lot of code there. The talk just before coffee in this room, the speaker said that he didn't believe in beautiful programs. I do believe in beautiful programs, and I think these are beautiful programs. Nice, short, elegant, and surprising programs. So they're very much like poems, or even like puns, that they make you surprise you in what you can say in a small number of words. So how do they work? The one that turns the concrete thing into the Profunctor thing is the easier one to make. If you've got to define an optic PABST, which is to say you've got to be able to turn a PAB into a PST, and happily you're given a function from S to A and a function from B to T. So if you've got a function from S to A and a PAB and a function from B to T, you can just use DIMAP, and that will stick the little adapters on either side of your Profunctor object, the transformer, and make the PST. So that's what the function adapter C to P does. It just uses DIMAP and just puts the two components O and I on either side of the transformer. The one in the opposite direction, adapter P to C, is a bit cryptic. If I know how to turn PABs into PSTs, how can I make the from function and the to function? Well, here's a very clever way. I have to make an adapter ABST, and it so happens that adapter AB is itself a Profunctor, and this is how to do a DIBAP for adapters. It's just function composition. So that means what I have to produce is PST, where P is the Profunctor adapter AB. And I'm given a gadget that will, L, that produces PSTs for me if I give it PABs. So if I can make a plain, ordinary, concrete adapter of type adapter ABAB, L will lift that to make an adapter ABST. That's what L does. It lifts PABs to make PSTs. So how can I make an adapter ABAB? Well, this is an adapter that takes an A in and produces an A out, and then in one direction, and takes a B in and produces a B out in the other direction. So it's just a pair of identity functions. So this is the kind of very trivial adapter that doesn't do any adapting. It's a PABAB, so it's an adapter ABAB, which is a PAB, and the L then turns that into a PST. So it just gives me the right type. It couldn't be any simpler or sweeter than that. And it's kind of surprising that that works, but this is precisely what you need. And then you can do all the equational reasoning and show that these two functions are indeed each other's inverses. So that's the Profunctor representation of adapters. It's a higher order function, if you like. It turns one kind of transformer into another kind of transformer. What about the other ones? Well, it's the same trick. And I'm not going to show the definitions. I'm just going to show the types. Once you've got the types, you can work out what the definitions are, perhaps. But the Profunctor definition of lenses is just the same, except we impose a stronger condition that has to work not for, what it can assume about the P is not only that it's a profunctor, it's a Cartesian profunctor. And that means it has a mechanism for threading stuff around the side, which is what you need to do in order to define lenses. For prisms, it's allowed to assume the P is not just a profunctor, but a co-Cartesian one. And that's to do with choices. And that's the mechanism you need in order to define prisms. And traversals, where you need this co-Cartesian and something else that I haven't shown you. But again, that works out. And if you want the details, then you should read the paper, and I'll give a link at the end of the talk. So that's the clever bit. Here's the payoff. So recall we had this lens onto the left-hand component of a pair. The lens pi1 gives you access to the A in an A, C pair. I'm going to turn that into its profunctor version. And I just do that using my, my conversion function that turns concrete lenses into profunctor lenses. If you unpack what that does, what I get, I could have written it instead from first principles, it's something that turns a PAB into a P A cross C, B cross C. So if you know how to act on the A's, this is how to act on the A's in an A cross C pair. And it has to work for any P, but it can assume the P is Cartesian, is a Cartesian profunctor. Now, the definition is not long, but it is also not obvious. And I couldn't have written that, I couldn't have come up with that myself without having gone through the route of figuring out the transformations, the conversion functions. But you don't need to write all this complicated stuff because there's a converter that does it for you. Similarly, there's a converter for prisms. So I'm going to turn my concrete prism onto the element of an optional type into the profunctor representation. And I'm just going to use the converter to do that. And then here's what I can do. To get access onto the A in a nested pair, an ACD nested pair, I just use pi1 twice. So with a profunctor representation, pi p1 is a function, and I just compose that function with itself, and it has precisely the right type and precisely the right behavior. That's what all you need to do is compose it. And that's so much easier than taking the record apart and doing clunky stuff with the functions in the record and then making a new record out of it. Better still, I can compose my lens with my prism. They're just functions, they just compose. And there's no rocket science to it. Again, it's just surprising that it works. So the composed with pi p1 in their profunctor representations says if you know how to transform A's into B's, then you can do that where the A is possibly buried in the left-hand component of an AC pair. And again, I couldn't have written the function that did that from first principles, but I can get it quite easily just by composing two things that I can get from converters. So if I wanted to square the 3 in this 3, 4, 5, pi p1 compose pi p1 does it. And if I want to square the 3 in this optional 3, 4, this present 3, 4, then the p after pi p1 just does it. Note that in the heterogeneous case here, what I've got is something that works for turning PABs into PSTs, and it's not a lens and it's not a prism because it's got a different set of constraints. But the nice thing about type class constraints is if you want more of them, you just add them. They just conjoin. So that's it. If you want the full details, you should read the paper, as I say. I've shown it in Haskell. It doesn't have to be in Haskell, but there aren't many languages in which you can do this. The thing that you need is generics of higher kind. So I need things like generic profunctors and applicative functors. So these are not types, they're operations on types. So Haskell has that, and Scala has that, but I don't know of any other language that has that. So it's not, you're not limited to Haskell, but you're limited to Haskell and Scala as far as I know. You might also think of this as a kind of fancy kind of generic programming that I've called data type generic programming in the past. And these features, these generics of a higher kind, are necessary for doing data type generic programming, for getting certain kinds of modularity. So I think this is a really cool feature, and I think data type generic programming is fun, and I think more languages should support this kind of thing. So to conclude, there are obvious, fairly obvious concrete representations of these data accessors, but they're not modular. The Profunctor representation is very nicely modular. What you get is a separation of concerns saying where you want to do some data access from what you want to do. Remember squaring the 3 in a 3, 4, 5 pair. I can say it's the left-hand component for the left-hand component, and then somewhere else say square it. So you might think of these also as first-class composable references into data structures. So the credits, this is, as I say, was Matthew's undergraduate work, and Matthew is now doing a PhD at Bristol with Nick Wu. The ideas are out there. They're mostly not ours, so we've been harvesting lots of blog posts and IRC chat comments and things. And the paper was presented at the new programming conference in Brussels in April, and if you want a copy, you can go to my webpage. So I'm very happy to take any questions.
Hi. Great
Hi.
talk.
Thank you.
Are you familiar with PureScript?
Yes.
So PureScript has a Profunctor optics library.
That's one of the ones we borrowed from.
So I was wondering, this is maybe only tangentially related, but in PureScript, the type classes that you referred to as Cartesian and co-Cartesian are called strong and choice.
Yes.
Could you explain the choice of names?
So we started off with strong and choice. We borrowed their names, but they're curiously, the constraints are duals to each other. They're about sums and products, which are categorically they're dual ideas. But strong and choice are not dual words. They're mixing metaphors. So we tried to think of something else, and I consulted wiser category theorists, and they said these things are Cartesian. That's what the category theorists called them, and co-Cartesian is obviously the dual of Cartesian.
Thank you.
So it's just nicer names.
Hi. If you can I go back on the first slides when you present the first example, which has some problems.
This one. Or do you want
for composing? Yeah. With the diagrams.
Oh, the diagrams. Yeah. Sorry.
The one with the ST and AB.
Okay.
Yeah.
These diagrams.
Before traverse. Yeah.
So that's for prisms. That's for lenses.
Yeah. So prism is basically a data type representing. So the function that you have to give it are those that transform the, for example, for the prism, the superclass into a subclass, or how to build.
Right. So they're the downcaster and the upcaster.
Okay.
Yeah.
So, but after all the machinery, you just have to provide those.
Yes.
Okay.
Yes. Yeah. Thank you. So you can build a concrete prism out of these two functions, the downcaster and the upcaster, and then you can apply my converter that turns it into its Profunctor representation. Yeah.
Well, since the next session is actually cancelled, then we have 14 minutes for questions.
I can do the whole talk again if you want.
Any more questions?
How much of this is implemented and where?
How much of it is implemented? Everything I've shown you is implemented. on the slides, if nowhere else. But but actually, if you go and find the paper, it includes the link to all the code. The paper is a literate Haskell script, and so the definitions of the paper are extracted from the script, and they're all there. It all type checks. It all runs. There's a link to download it, but it's only, we haven't done anything very much with it. It's only 30 lines of code or something.
Is there an implementation on Hackage or something?
No, we didn't go that far, but it's, as I say, it's only 30 lines. It doesn't seem worth making a whole package out of it.
Yeah, but like I think the part you or like if you want to use it, you're also interested is like generating like the lenses for records and stuff like that, all the template Haskell stuff.
So I should say that one of the people we borrowed from greatly is Edward Komet, and he has much better developed lens libraries, which do all sorts of clever things with template Haskell to generate the basic things for records, for fields of records. So that's hugely better engineered than anything we've done, and it's a big library. It's got 40 type classes and 100 functions in it, or something like that. We've only given you. You could retype them. It wouldn't take you very long. In fact, it might take you less time to retype all this than to find the paper.
Okay, thank you.
I believe Russell O'Connor has a Profunctor optics library on Hackage now, and I cannot recall the name off the top of my head, but it's something lens.
Mezzo lens is probably the...
yeah, probably.
Mezzo.
Mezzo, like medium-sized.
Anyone else? If not, send the speaker again. And the next section is going to be here at 5:15.
They do compose homogeneously, but only in a clunky way. So I'm going to fix both of those problems by showing you a different representation. And this representation is in terms of these things called profunctors, which are rather cool. And it's a very slick presentation, and it will allow us to compose lenses easily with other lenses, and more importantly, to compose lenses with prisms and lenses with traversals and adapters with prisms and so on. So you'll get much better compositionality of these data access mechanisms. So I call this modular data access mechanisms. So this is one way of looking at this is a kind of bidirectional programming style. You express the getters and the setters in one go by saying whereabouts in the structure you are. It's kind of like a pointer into a structure, I've been doing some work recently on bidirectional programming languages, which let you express in one go a program that can be read in two different directions, sort of the get direction and the set direction. But I recently discovered that, it occurred to me that a nicer logo for this is the former British Rail logo. Now, maybe you can't see this if I'm sitting down, but here's my my bidirectional T-shirt. So here's lenses. The getter and the setter I've called view and update here. The For the video recording, I need to be sitting down, otherwise the camera doesn't get the top of my head. So this is why I'm sitting down here. I'm going to talk about these things called Profunctor optics. This is work that I've been doing with Matthew Pickering and Nicholas Wu. Matthew is an undergraduate student of mine. He did his project on this, and it's very nice work, but it's mostly his work, and I get to give the talk about it. So what this is about is lenses for access into data structures. So a lens, the easiest thing to think of with a lens is if you have a pair with two values, a left value and a right value, you might want to have access onto the left-hand value in that pair. And in particular, you might want to be able to get the left-hand value from the pair and then to set a new left-hand value in the pair. So there's two functions involved, a getter and a setter, to get access onto the left-hand component of a pair. So lenses do this for any product type. It can be a field of a record, it can be the third element of a list. So any projection works through a lens. But there is a dual to this for some types. These things are called prisms, and I'll show you concrete definitions of these in examples later. And lenses and prisms are have collectively been called optics, and there are some more things within. So, I'm going to call that lens pi 1. So that's lenses. The dual prisms is for some types. So a sum type, think for example an object-oriented superclass with several concrete subclasses, and a prism will give you access to one of these things as the subclass. So maybe you've got shapes and you've got squares and circles, and you've got something that you want to do to a circle, and what you're given is a shape. So it's got the wrong type. So you need to get access to that thing as a circle, and so there's a downcast method that will give you from a shape to a circle, and an upcast from the circle back to the shape again. So here it's dual, so it's the other way around. It's the upcast that is the obvious thing. The upcast always succeeds. So I've called that build here. That takes the value that you've changed it into and upcasts it back to the enclosing type, the context. Matching is the complicated thing. So matching, like downcasting in OO terminology, might fail. You might have a shape and try to downcast it to a circle, and it might be a square. The downcast might fail. So this generates a sum, whereas the lens, the update function, consumed a product. So that's the duality coming through. And if you look at the bottom right, in the remit of optics, there are also things called adapters and things called traversals. And I will also tell you what those things are. And there are two problems with the obvious way of representing these, where you represent a lens as the two functions, the getter function and the setter function. One problem is that these optics are not closed under what are called heterogeneous composition on the slide. By that I mean you might want to put together a lens and a prism. A lens will give you access into part of a product type, and maybe there's a sum type within that. So to get access within a sum within a product, you would hope to be able to compose a lens and a prism somehow, saying how to get through each part. But the problem is, the thing that gives you access into a sum, into a product, is not a lens, and it's not a prism. And I'll show why that's the case. So you can't express that as a lens, and you can't express it as a prism. These things are just not within the language of expressible stuff. And a second problem is, suppose you wanted to put together a lens with another lens. So you've got access within the left-hand component of the pair, and maybe that is itself a pair, and you want to get at the left-hand component of that. So it's the left component of the left component of a nested pair. That is a lens, and you can make it out of putting together two lenses, but it's a bit clumsy to do so. you have to take the lens apart into its getter and setter functions. If you have a structure S and it has an A component within it, the view function the view function is a function from the whole structure S to the component. It extracts the components within it, the A. And if you want to change that component to a B and put it back, you'll get a new structure which will be might be of a different type, T. So the update function takes the new component B and the old structure in which it appeared, S, and produces a new structure. So maybe this is an integer character pair, and you take out the integer and put a float in its place, then you'll get a float character pair as the result. So the output type might be different from the input type. So I've captured this as a piece of Haskell. It's a record with two fields, each of which is a function. And there's a picture at the bottom right of the slide that shows those two functions. So the view function is just a plain ordinary function from S to A, and the update function takes two inputs. It takes a B on the right-hand side and the old S on the left-hand side and produces a T as the result. So in the middle of the slide is an example lens. This is the lens onto the A component of an A cross C pair, and the view function gives you the first component of the pair, and the update function takes a new value for the first component of the pair and an old pair and throws the old left-hand component away and puts the new left-hand component in its place.